Hi everyone, this lesson is about complex numbers, how we represent them in the Argand plane, and what the modulus and the argument of a complex number are. So if we take a complex number z, like just a generic a plus b times I, then we represent this sometimes on a two-dimensional plane where this is the real axis, sometimes called x, and it's a capital X, and this is the imaginary part on the vertical axis, sometimes called yi. So the x and the y are capitalised to make them distinct from a Cartesian plane, and this is called an Argand plane, named after the person who first proposed the use. So the value of a represents the real part, so we would move to wherever the value of a is along the real axis. The value of b represents the imaginary part of the complex number, and so together there is a coordinate point, a plus bi, and we often represent these things as a vector. Nice. Now, as with any vector, the a and the b would represent the rectangular coordinates, because you could imagine little dotted lines here completing a rectangle, and the vector is the diagonal from the origin of the Argand plane to the tip of the vector. Instead, we sometimes refer to the modulus and the argument. The modulus, sometimes just written as mod z, also sometimes written like this. It represents the length of the vector, and so that would be, by Pythagoras, a squared plus b squared, and we take the square root. The argument of z, it's the angle, and so we would use trigonometry to find the inverse tan ratio of b divided by a. That's, in a nutshell, what the Argand plane is about. There is a real axis horizontally, labelled capital X. There is an imaginary axis vertically, labelled capital YI, and then a complex number such as this one here that I've got, Z. It can be represented on the Argand plane as a vector. There is the length of the thing, called modulus. There is the angle compared to the real axis, which is called the argument. And they behave just like vectors. We can add them, we can subtract them, we can do all those normal things that we do with vectors with these complex numbers. Now, I'll just show you a quick example. Let's imagine we have a complex number. Oh, why am I in red? Let's have a complex number z1, which is root 3 plus I. We have another complex number, z2, which is 4 minus 4i. And the question that I have for you is, find the angle between the two vectors representing these complex numbers. The first step is to do a sketch. So root 3 is about 1.73, and 1 obviously is less than that. So my first complex number is here, and there would be an argument for that. Let's call that argument theta 1. That's complex number z1. The second complex number, 4, that's way over here. Negative 4 is way down here. So there's my second complex number. Call that z2, and there would be an argument for that one, theta 2. So I think the way to find the angle between these vectors is to find the argument for each, and then we'll decide what we do after that. So theta 1 is the argument of complex number z1, and so that is root 3. Oh, what am I talking about? It's the argument, it's not the modulus. It's the inverse tan of 1 over root 3. Now, hopefully you know that if that's 1 and that's root 3, that's 2, and that comes to 30 degrees. You could, of course, use your calculator if you wanted. Theta 2, on the other hand, is the argument of complex number Z2, which is the inverse tan of negative 4 over 4. And I hope you realise that comes to negative 45 degrees. Negative, of course, indicating that this turns downwards from the real axis and this one turns upwards from the real axis. So what does that mean for the angle between our two complex numbers? Well, I think it's pretty obvious that we will need to go 30 and then we have to add 45, even though it's downwards, just the other way. So the angle between them, which I'll just label as a different angle, phi, would be 75 degrees. That's just a little example of how we might use the arguments in this case. Now, I wanted to show you on the CG50 how we could do this. The CG50 can operate with complex numbers. So if I wanted to do, if I go options, then under the complex menu, I have here the argument. So I'll write argument, then I'll put my first complex number, root 3 plus I. I could either just press the I, or I'm still under the square root sign, silly me. Root 3, I'm still there, try again, plus I. And look at that, it's 30 degrees like we thought. Now I'll do the argument. Oh, I'm sorry, it says absolute. It's this, that means that's the calculator's shorthand for modulus. I meant to press argument then. And this time we'll go for subtract 4i. And we get negative 45 degrees, just like we thought. So the calculator can assist you to do these, even if you're not quite sure of what the inverse tan of this is or the inverse tan of this is. You can just go straight for the argument function, but you could also just go inverse tan, couldn't you? So that's a very quick introduction to the Argand plane, how we draw complex numbers as vectors, and how we can calculate the length of them, which is called modulus, and the angle, which is called the argument. That's enough for now. Thanks for watching.